gentlemen, fellow critical thinkers. Back home, I am called a critical thinker because we cannot pronounce tha. But the tha is pronounced as ta. My paper is on pages 5, 6, 7 for the proceedings. Let me start by, I am Musa Abdullahi from Nigeria. Let me start by thanking the organizers of this conference for making it possible for me once more to be in the United States of America, a great country. I am particularly grateful to Mr. Hope for helping in editing the papers. The first paper is on aberration of electric field.
Closer to the microphone, please.
Aberration of electric field and accelerated motion of an electron with constant mass.
Closer, please.
Go to slide 2. We must all have heard about aberration of light, discovered by the English astronomer James Bradley as far back as 1725. This is one of the most significant discoveries in science, but somehow now relegated to the background in favor of special relativity. The diagram here depicts aberration of electric field. The aberration of light comes because of the finished speed of light. Electrical force is also transmitted with the speed of light. Therefore, an electric charge moving in an electric field should be subject to aberration of electric field. An electron of charge minus E and mass m moving with velocity v at an angle theta to the force of attraction due to electric field E is subject to aberration of electric field. The electric field appears along NP, not along the line joining the source charge and the moving charge. It appears along NP such that sine alpha is equal to V over C sine theta. You can get this by applying the sine rule to this triangle, OPN. Oh. What happened?
I think maybe.
Okay.
No,
Okay. The cursor is not on. Thank you.
Sure.
So our starting point is this diagram depicting aberration of electric field, from which this equation is obtained. Slide 3. The relative velocity between an electric charge moving with velocity v and the electrical force propagated with velocity c is c minus v. And the force of attraction between the charge q and the electron e, the relative velocity between the charge q, the electron moving with velocity c, with velocity v, and the charge q is this expression, c squared plus v squared minus 2cv cos theta minus alpha. Theta minus alpha is the angle between the vectors c and v. For theta, the electron can move with acceleration in the direction p or it can move with deceleration in the direction OP, or it can go round O with theta equal to pi by 2, 90 degrees. For theta is equal to 0, there is accelerated motion with relative speed c minus v. For theta is equal to pi, there is decelerated motion with relative speed c plus v. For theta is equal to pi by 2 radians, there is motion in a circle with relative speed the square root of c minus v. You get this if you substitute the angle theta and alpha in this equation. For acceleration, the relative speed is c minus v. For deceleration, the relative speed between the force on the electron and the electron moving, if it is moving against the force, relative speed c minus v. If it is moving at the right angle to the force, the relative speed is square root of c squared minus v squared. The accelerating force is given by this equation. You can immediately see that if the electron is moving with the same velocity as the accelerating force, the force cannot impact on it. The force cannot catch up with the electron, and therefore the electron can be accelerated to the speed of light and no faster. Here we have the maximum speed of light coming, not as a result of mass increasing to become infinitely large at the speed of light, but as a result of the accelerating force decreasing with speed, reducing to 0 at the speed of light. So if we have this equation for the force on the moving electron, for theta is equal to 0, the accelerating force is given by this equation, equal to m dv by dt. For theta is equal to pi radians, the accelerating force is given by this equation. For theta is equal to pi by 2 radians, 90 degrees, the accelerating force is given by this equation. Now you can solve this equation. These are first order differential equations. You can solve them for a constant electric field and show that the maximum velocity, the maximum speed to which the electron can be accelerated is the speed of light. For theta is equal to 5/2 radians, there is motion in a circle with the accelerating force given by this equation. Motion in a circle is necessarily constant. If a particle moves in a circle,
Closer, please.
if a particle moves in a circle, it moves with constant speed. Radiation reaction force and radiation power. Now, an electron stationary in an electric field has an impressed force on it, the charge times the electric field. This is the force on an electron stationary in an electric field. If it moves in the field, the force becomes this equation. Depends on the relative speed between the force and the moving electron. Radiation power, the radiation reaction force is the accelerating force minus the impressed force. The force of the electron is maximum if it is stationary. If it moves, the force is less than the impressed force. The difference is the radiation reaction force. So, if you subtract minus EE from this, you get this equation as the radiation reaction force. The scalar product of the radiation reaction force and the velocity gives you the radiation power. If you do that, this is the equation you get as the radiation power. You can show this to be the case with respect to this diagram. This is the radiation power for an electron moving in an electric field. If theta is equal to 0, that is, if it is moving along the field or against the field, the radiation power is given by this equation, EeV squared over C. If theta is 90 degrees, pi over 2 radians, the radiation power is 0. So, circular revolution of an electron round a central force of attraction is with 0 radiation power. It's stable. This makes Rutherford's model of the hydrogen atom inherently stable. There was no need for both quantum mechanics to stabilize it. This is one of the most important outcomes of this paper. Aberration force of an electron moving with velocity v, the accelerating force, as we said, is given by this equation. For theta is equal to 90 degrees, we have the accelerating force given by this equation. The accelerating force reduces to 0 at the speed of light c. Whether it is moving linearly along the electric field or against the electric field, or moving in a circle perpendicular to the electric field, the accelerating force becomes 0 at the speed of light. The magnitude of the electric force is given by this equation, from which we can obtain Lorentz factor as the ratio of the electrostatic force EE and the accelerating force in the circular motion, NB squared over R. This makes the Lorentz vector gamma simply the result of a particle moving perpendicular to an electric field, or motion of an observer perpendicular to the direction of a ray of light. The Lorentz vector gamma here has nothing to do with mass. Neither has it anything to do with length, length construction, or time dilation. It's simply the result of motion of a particle, a charged particle, perpendicular to an electric field. This is another important proposition of this paper. Well, this gamma vector is so ubiquitous, you see it everywhere. But what we are saying here, the Lorentz vector is simply the ratio of the electrostatic force, EE, and the accelerating force, mv squared over r, of a particle moving in a circle perpendicular to a radial electric field. Results and discussion. Aberration of light is a direct indication of the relativity or speed of light with respect to a moving observer, contrary to the theory of special relativity. It makes you wonder,
Closer, please.
if as far back as 1725, there was an experimental result, a result of observation, which clearly showed that you can add to or subtract from the speed of light. Why are we still bogged down with this relativistic concept of constancy of speed of light? You remove the constancy or speed of light from relativity, and the theory of special relativity comes tumbling down. Here we have over 200 years experiment which has shown that. And yet we are saying that c plus v, c the speed of light plus v is equal to c minus v. Against all, one has to subjugate one's common sense to agree with that. But here we have an experiment which really shows that this is not so. You can add to or subtract to the speed of light. Relative velocity between an electrical force transmitted with the velocity of light c with respect to an electron moving with velocity v is c minus v. The accelerating force decreases with velocity, reducing to zero at speed v equals c. An electrical force transmitted at the speed of light c cannot catch up and impact on an electron also moving with the speed of light. I mean, if you have a sailing boat, that sailing boat can be accelerated to the speed of the wind and no faster. The wind will keep impacting on it until the speed of the boat reaches the speed of the wind, and it can no longer impact on it. So a sailing boat can be accelerated to the speed of the wind and no faster. An electron or a charged particle can be accelerated to the speed of light and no faster, because at that speed the force on it becomes zero. It is much easier to deal with zero force at the speed of light than infinite mass at the speed of light. It is unfortunate that the relativity shows mass at the variant rather than force. To get the same effect, An infinite mass reduces to zero acceleration. Zero force reduces to zero acceleration. An electric field can accelerate a charged particle, such as an electron, with constant mass to the speed of light and no faster. Here, we have done away with infinite mass at the speed of light. Doing away with infinite mass will bring a lot of relief to physicists all over the world. Because what is an infinite mass? An infinite mass is the mass of the whole universe. Having such a mass, millions of such a mass, within the apparatus of laboratory, is unthinkable. Why is the limiting speed of light c? This is so because of radiation. As the electron is accelerated by an electric field, it radiates. The radiant energy is equal to the difference between kinetic energy and the potential energy. If an electron is accelerated, a charged particle is accelerated by an electric field, it loses potential energy. The difference between the potential energy lost and the kinetic energy, the potential energy lost and the kinetic energy gained is the energy radiated. The electron or the charged particle can be accelerated to the speed of light. At the speed of light, the amount of the potential energy lost is equal to the energy radiated, because there is no increase in speed. Conclusion: the paper has succeeded in introducing aberration of electric field, leading to an electrodynamics of a charged particle accelerated to the speed of light at constant mass and with emission of radiation. One can even say that the problem of physics today is related to non-recognition of aberration of light and aberration of electric field. Recommendation: aberration of light should be resurrected and restored to its rightful and significant place in physics, in contrast to the relativistic principle of constancy or speed of light for all observers, moving or stationary. Gentlemen, this is my paper. Thank you for listening.
Okay, questions?
I've got one. Does your electron move in a circular orbit or in a spherical shell?
In a circle.
Circle, not a shell, and it's not a spherical shell like they say in quantum mechanics.
No, in a circle.
Okay, so it's two-dimensional.
Yes.
Like an orbit.
Like an orbiting planet.
Well, I got a couple questions for you, Musa.
Yeah,
So these are kind of subjects that are dear to my heart, so I may give you a little hard time. But, you know, I do agree with some of the things about, say, aberration of light, but I'm not quite so sure about what you're saying about aberration of the electric field. Because as far as I know, the aberration of light is kind of an observational thing where the planet appears to not be where it actually is. But you're saying that's related something to the aberration of the electric field, which I could kind of see kind of doing the same thing, but once again, it would kind of be just an observational thing where someone looking to find the location of the electron might not see it in the same place. But you've got a bunch of equations in there, which admittedly I have no idea I'm not a mathematician, I can't verify whether any of that really makes any sense. So can you comment on what do you mean by the aberration of the electric field, and how is that? I'm still not quite sure I understand what's the significance of that is.
That's a very good question. Aberration of light, we may all be familiar with, where if you are observing a star, it appears displaced in the forward direction by the aberration angle. This is because of the finite speed of light. In the case of the aberration, is not dependent on distance. Aberration takes place even with nearer object. It need not be a far off star. The thing with near thing is that if they are so near, the angle is so minute that it cannot be detected. But aberration is not dependent on distance. Look at the formula by Bradley, sin alpha, that the angle of aberration is equal to V over C sin theta.
Closer, please.
It depends only on the angle at which you are moving, the angle between the instantaneous line joining the star and the observer. If you are moving at an angle theta, then the aberration angle alpha is equal to V over C sin theta. It's independent of the distance between the star.
Yeah, so my question is, we understand that, but what does that have to
If
do
you
with the
come
electric
to
field?
the case of electric field, an electric field is transmitted at the speed of light. Therefore, a charged particle moving in an electric field will be subject to aberration of electric field.
So how do we know that the electric field travels at the speed of light? I mean, that alone would be an interesting, has that been measured?
Well, could it have, we all know electric effects travel at the speed of light. I didn't measure it, of course, but I assume that it is so.
It's a
All
little bit,
electric
it's
effects.
a little bit hard to measure because, like, you know, you can measure the speed of light because you can turn on your light source and then you can see it traveling. But it's really kind of hard to turn on an electric source. Like, I can't just turn on a proton and then measure its effect across distance. I mean, personally, I think that the electric force does in fact travel at the speed of light, primarily because I think it is actually an electromagnetic effect. So, but I was just wondering whether you had any thoughts as to whether the electric field effect could be instantaneous, not unless you have any evidence to the contrary.
I don't have any experimental evidence, but could call it a hunch, and the electrical effects cannot travel at any other speed than that of light. If you switch a current, we know that within the speed of light, the effect is felt elsewhere at the speed of light.
All right, now, can you go back to your previous slide? So that shows your conclusions, but I noticed that probably the most controversial conclusion that you're coming to, which is that the electron can orbit without radiating, is not actually part of your 7, 8, or 9. So I was kind of wondering why is that?
An electron orbiting in a circle does not radiate. If an electron radiates in a circle,
Yeah, I know that you're saying that, but I'm curious as to why that isn't part of this last slide. You don't because I actually agree with a lot of this stuff, but I kind of violently disagree with this idea that the electron can orbit without radiating. So, but I just thought it was kind of curious that you don't have that in your last slide.
now if an electron is moving in a circle, there is no change in potential energy, no change in kinetic energy, therefore no radiation. The radiation is the difference between the kinetic energy and the potential energy.
Well, see, I can't claim to know exactly how this stuff works, so maybe you can explain it, which is why is it we think that accelerating charges radiate? I mean, that's fundamentally what the problem here is, because when something is going in a circle, it's said to be accelerating is the problem. And anything undergoing acceleration has to be radiating is the classic argument. And so if it's radiating, then it has to actually spin down into the attracting charge. And I don't know, some catastrophe is supposed to happen. But still, the main question is, I don't understand why is it that anything being accelerated should radiate. You had the radiative equation there, and without understanding how that works, it's kind of hard to say whether something should radiate if it's going in a circle. Me personally, I don't see it, but maybe you can comment. Why is it something that's accelerating should be radiating?
Well, yes, an electron, a particle moving in a circle, is an acceleration towards the center. And on this basis, we have Lamont equation of radiation.
Yes, that's the classical analysis that they do, saying that this thing's got to be radiating. So what are you saying that's saying that that's not true, right? You're saying something about...
I'm saying that it's not true. It doesn't radiate.
You're saying there's something about the aberration of the electric charge or field that somehow circumvents that calculation.
There is no change in potential energy for a particle moving in a circle. Motion in a circle is necessarily at a constant speed. Once the motion is not a constant speed, you have an ellipse, you have an elliptic orbit. But if it is circular, there is no change in kinetic energy and no change in potential energy.
But it seems that doesn't really matter, because the radiation isn't due...
Is radiation energy?
Yeah, Bob wants to know, is radiation energy? I mean, and what kind of radiation is this? This is the other mystery. I would presume it's some kind of electromagnetic wave or something, but...
If you have an electron moving in a circle around a nucleus, as in the Rutherford nuclear model, as long as it's moving in a circle, no radiation. But if it is dislodged from the circular orbit, then it radiates. It radiates at a frequency equal to the frequency of revolution of the particle. It radiates and then reverts back to the stable circular orbit.
Well, I can bring up one counterexample, which is positronium. So positronium is a simple electron orbiting a positron. And that is known, I believe, to act classically, which it does radiate, and the electron does go crashing down on the positron. It's not a stable system. So why is it that positronium is not stable? Because it's exactly the same charge system as a hydrogen atom, which is one positive charge in the center and one electron. So you think if that's stable, you'd think positronium would be equally stable, but it's not. It almost immediately annihilates.
Well, maybe so. Then we have some difficulties here and there, and we keep talking until we sort them out.
Well, it might be an interesting point, but like I said, I can't really validate the equations that you have that justify the zero radiation, because I know eventually there's some thing there in your slides that says equal zero, right? And that's how you're saying that there's zero radiation power. But considering I don't understand where the radiation comes from, I don't know what kind of radiation it is, and I know there are other similar systems that do collapse, then I'm just kind of skeptical about whether that's true or not. I guess I'm kind of skeptical about the mainstream position that it has to radiate, and I'm skeptical about your position saying that it's stable.
Well, thank you for sharing my thoughts.
I have a question.
You're saying that you allow a variable light speed of light, is that correct? C plus V, was I understanding that correctly?
Beg your pardon?
A variable speed of light, that is C plus, you were saying that C is not a constant?
No, C is a constant. C is a constant. But C minus V is not a constant. It depends on V. As V increases, the relative speed changes, and it can be 0 if V is equal to C.
Okay, maybe I think I answered you answered correctly. I think I was asking the question wrong. So there are things that we associate in mainstream as going with C, but you're saying that those objects aren't constant C? Is that what I'm understanding then?
C as the speed of light, the speed at which an electrical force is transmitted, is C. See? But what relativity is saying, if an observer moves with any speed, the speed of light relative to that observer is still C, according to special relativity. What we are saying that is not C. If you move in the direction of light, your relative speed of light is C minus V. If you move against...
Are you talking about observers or actual objects? That's what I'm getting. Okay, if you're saying C plus V, what is the V velocity of?
V is the velocity of the observer. If you are talking of light, in this particular case, V is the velocity of the charge moving in the electric field.
So charges can go faster than speed of light or slower?
Again,
Charges can go faster or slower than the speed of light, is what you're saying then?
no.
Then I guess I'm not understanding C plus V or C minus V then. Could you?
In the electrical force, if you have an object punching you at a certain speed, that you can accelerate that object to the speed with which you are pushing it, and no faster. So an electrical force is transmitted at the speed of light. So if an electron or a charged particle moves with a certain speed in the electric field, the force is punching it at a speed of C minus V. If the particle is moving at a speed C, and the force is also moving at a speed C, it can no longer impact on it. It moves, it can be accelerated to the speed of light and no faster. The speed of light still remains a C.
Okay.
But relative to an observer or to a moving electron or a moving charged particle is not C.
No, I get that. So it's like a particle accelerator where, yes, if you are using C to accelerate, you're never going to get something going faster than C.
You can never get something.
Right. Okay, all right, gotcha, I got you. I just wanted to, I wasn't understanding that, so, okay, thank you.
Sorry, you have been wanting.
That's okay. My answer is directly.
Let's get a microphone to him because we can't hear the question. Somebody get a mic to him.
Okay.
Who's coming, Dave?
Okay, yeah.
My answer is more directly to Franklin's question. How do you know the electric field travel at a certain speed, such as the speed of light? And I would like to say that it should be easy. Number one, on the theory, we know that electrical magnetic wave is the mother of light. So if light has a certain speed, c, I believe electrical field transmitted at the same speed like c2. But this is on theory. On practice, you can put the charge over here and 300,000 kilometers away, there you put an instrument to measure intensity of your electrical field from here, and then you move this source to a certain distance at a certain speed, and correspondingly at this point, also 300,000 kilometers away from the charge source, if the intensity here measure at the same intensity like what you measure here, after this source complete this movement, and then you can test how fast this point can get to the same intensity like what is observed at this point. If the electrical field propagates slower than the speed of light, and then when this source comes over here, at this point you don't measure the same intensity like what you get over here. But if it travels, it propagates faster than the speed of light, at this point you would have the same intensity like at this point, even ahead of the charge movement. That's my point.
Thank you. Thank you.
Well, I would agree that that would be a valid test, but has anyone actually done that? Because that's in principle a really, really hard experiment to do. I mean, to measure, like, you can't really measure the force of one proton that you moved like 1 meter, and then measure the field strength to do that. I mean, I think that would have been perfectly valid if you could do that. You just take one charge and move it around. But in principle, I've actually just, never actually seen a real experiment that tries to prove the speed of the electric field in kind of a rigorous way. But yeah, in principle, yeah, I would totally agree that that's the way to do it, but I'd just like to see an actual experiment trying to do that.
You have to push the button up. Oh.
Yeah, you gotta push.
Okay. What I am saying is that we can devise that kind of experiment to verify the speed of that electrical field propagation speed.
Yeah, it can in principle be done. I totally agree with that.
I don't mean that anybody has done this.
Yeah.
Okay, thank you.
I think it's just an interesting question about what we think our assumptions are.
Well, we have to start with an assumption, and that when we are proved wrong, we change our assumptions. The reality is always the reality.
And I did have one other comment based on what you were just talking about, which is the speed limit of c. And like you, I thought that no object can be pushed faster than the thing that's pushing it.
Yes.
But when I discussed it with Bill Lucas, he does bring up the point that the amount of energy that particle delivers is much greater than you would expect for the speed that it's actually attaining. So if the speed limit is c, you would think that the maximum limit for the energy that thing can deliver is 1/2 mc squared. You think that would be the maximum amount of energy that can be delivered. But in fact, the amount of energy delivered by that particle as it approaches c is much, much greater. So you can imagine them firing an electron against a steel plate, and you can measure the reaction force. But what happens is that as the electron gets to the higher speed, it can hit that plate with like the force of a baseball. Much, much greater than what you expect. So somehow the energy is being absorbed into the particle. It's not a linear thing. So that's why they have to say that the mass increases or something in order to say that the kinetic energy formula is still valid. But it could be something else. But like I said, they choose to play with the mass term to make, because they say as you accelerate things, the mass of the electron gets bigger. So the mass of the electron could become 23 pounds as it approaches the speed of light. but that's just a measure of, based on its actual velocity, how much kinetic energy is observed impacting the target.
Well, that's when they're using relativistic kinematics. And if you use relativistic kinematics, you have speed changing energy, whether you want to interpret that as mass or not. Or you can get rid of relativity, use autodynamic equations, and you don't need that and you don't see that. So it's not so much that it's observed, it's that in the end game, they do not see mass increase or even energy increase as they're accelerating particles. This is from a Stanford linear accelerator person that I had in my movie. But they also, what they say is, oh, by the way, we use relativistic kinematic equations, and therefore there's more energy, therefore, at the end. When in reality, the equations they use put into it. So it's a little bit, I know what Bill's saying, but I don't necessarily agree with that. But let's wrap that up, I think, for this talk for today. And thank Musa. We have another talk coming up with Musa. So thank you very much.
The second paper.
Yes, thank you very much.